next time. Okay, so we talked about the general matrix formulation for these non-parametric estimation problems as being something of the following sort. So z hat is w times y. And now the idea here was that since we started with just some kernel, this k of xi and xj, we ended up with this w, and we wanted to now understand how we could possibly improve the performance of this basic filter by playing various tricks. And we talked about one possibility being estimation of the signal-to-noise ratio, another one being adjusting the parameters of particularly the bandwidth of the kernel to try to achieve this optimality criterion. And let me remind you, the optimality criterion for this was that this the eigenvalues of lambda had to satisfy 1 over 1 plus SNR I to the minus 1. Okay? And so generically, for any choice of kernel, when you start off, you're not going to get the eigenvalues of W to satisfy this condition. So we wanted to see how we could maybe get close to this possibility. Okay, so one of these possibilities was repeated application of this filter. And this is the idea that we call diffusion for reasons that will become clear later on in this lecture. So the idea was that we would construct an iteration of the following kind. Okay, so you don't just satisfy yourself with a single application of W. You apply W again and again, and this is what you get. You apply W again to the last estimate, and so on. And just to be clear, the W here is fixed. So in other words, you compute it once at the beginning, and then you just apply it again and again. An alternative version of doing this would be to compute W on the last estimate, and then apply it again. Now it turns out those things actually don't behave all that differently. But the analysis of the second kind, namely when W is recomputed, is somewhat more complicated, so we're not going to discuss it here. Okay, so with this in place, if you remember, we wanted to study the behavior of this filter, and of course another way to write this would be W to the k times y, where y is the original noisy data, which is equal to this the clean image, or the regression function plus some noise. Okay, and remember, we assumed that the noise here was zero mean. All right, so with this, we used the eigendecomposition of W. We wrote W to the k as this V, S to the k, V transpose, where V is an orthonormal matrix, and the eigenvalues of W to the k are now the eigenvalues that were there before, the lambda i's, raised to the kth power. So the eigenvalues of this guy are lambda I to the k. Okay, and so using this, then we wrote down the mean squared error as a function of the kth iteration, and that is the sum I equals 1 to n, lambda I to the k minus 1 squared, 0I squared plus sigma squared lambda I to the 2k. And just to remind you, these coefficients B0I are the coefficients of the signal Z, which you don't know, in the basis, which are the columns of V. Yeah?
Is S guaranteed to have at least one diagonal element that is 1?
This S?
Yes.
Yeah, so W, this is one of the properties that we discussed in the last lecture, was that the matrix W is a stochastic matrix, which means that its rows sum up to 1. And when you have a positive definite, symmetric positive definite matrix with rows summing up to 1, then it's not only that one of its eigenvalues is equal to 1, actually the largest eigenvalue is equal to 1. I guess you weren't here last time.
No, I mean, I watched the lecture, but the thing that bugs me a little is you make the you make that as an approximation.
Don't worry about the approximation, okay?
The approximation always holds.
Yes. Don't pick on the approximation. The approximation is a red herring that you don't need to worry about. It's true.
Okay.
Even if, in fact, even if the approximation is not true, you still have the largest eigenvalue is equal to 1. The only approximation I'm making here is whether the matrix is symmetric or not. Okay, I don't need the approximation specifically to guarantee that the largest eigenvalue is equal to 1. Okay? That always holds, because the row sums to 1. I mean, the reasoning is kind of obvious, because if the row sums up to 1, then you can write that as W times a vector of 1s is equal to 1, right?
Yeah.
This, by definition, tells you that one of the eigenvalues is 1. So the only other thing I have to prove is that that's the largest eigenvalue, and that doesn't have really anything to do with the approximation.
I mean, what I was going to get to is, as long as there's not an eigenvalue that is 1, you can basically take a fractional power of the matrix.
Well, I don't need a fractional power of the matrix.
But, well, in the last lecture you also said that by going through this iterative process of going through this Z of K's, you can get to, I guess, the optimal diffusion. You can more or less skip the optimal diffusion.
Yeah, you may skip the other. Yeah, you can go from one integer k to the next integer k. Right.
Right, but if there's no, if there are no eigenvalues that equal to 1, then you can basically take fractional powers and you can.
Well, there is an eigenvalue that's equal to 1.
Yeah.
So you can't do that. Okay, so here's the mean squared error. And if you remember, so B0I, again, you write the vector Z as the sum of the columns of V, which are VI, times these coefficients B0I, I equals 1 to n. And if you remember that I told you these VI's are basically like the Fourier coefficients. I'm sorry, the Fourier basis, and the V0I's are like the Fourier coefficients. Okay, so this thing has two pieces. This piece here is the bias squared as a function of iteration. And this piece here is the variance. Okay. Now if you look at this, what you'll notice is that because the eigenvalues lambda I are all between 0 and 1, then what happens is that as you increase the power k, this term here actually increases. Okay? So the bias goes up with iteration, and the variance goes down with iteration. Again, because the lambda i's are less than 1. And this is not terribly surprising to some extent, because if you remember, we showed last time that this W to the K essentially converges to a matrix of rank 1. And then if you multiply that matrix of rank 1, not only does it approach a matrix of rank 1, that matrix also has constant rows. Okay? So when you multiply it by y, what you end up with is a constant image at the end. So this is consistent with that intuition, because what it says is that the variance continues to decay until you get a flat image. Okay? All right, so then one question that comes up is, if you look at this expression, you might ask, okay, with the first application of W, which is this for Z0, right? So W times Y, you would get some mean squared error, right? Now, I have sort of, I've just told you that if you apply W again, you may get a smaller mean squared error, but I haven't proved it. Right? I've just suggested this as one possible thing you could do. And so now the question I can ask is, in general, how can I guarantee that this procedure that I'm suggesting to you is in fact going to work, that it's going to in fact decrease the mean squared error as I continue this iteration? So let's take a quick look. So when will this iteration improve the mean squared error? Okay. Now, it's a little difficult to answer that question for the whole thing, but in fact, we can answer the question for one term at a time. In other words, for each I. So let me rewrite this equation in a slightly different form. Namely, let me just assume that I know this sigma squared. I assume that throughout anyway, so this is just the noise variance. And what I'm going to do is I'm going to divide everything by sigma squared. All right, so I'm going to define this mean squared error sub k. We're going to put a bar on top of it, and then define this as mean squared error k divided by sigma squared. Okay, and so then the right-hand side becomes the sum, I equals 1 to n, lambda I to the k minus 1 squared. And now this term is going to be b0i squared divided by sigma squared, which is nothing but the signal to noise ratio for the ith channel. Okay, plus lambda I to the 2k. Okay? Yeah.
We want to minimize this for a specific k.
Well, I'll get to that in a moment. So first, I want to show that even one iteration is going to improve the mean squared error. Okay? This thing, if you look at the way this function is, the form of this expression, basically, it's going to have one minimum, right? And so what it's going to do is, if it's going to have one minimum, if even at the first iteration it's going up, then it's not going to have a minimum, right? It's going to go up, and it's going to get worse. So the first thing I need to do is, if it has a minimum, I have to make sure that at the first iteration it's going to go down. So that's the first thing that I want to look at and see what happens. And in fact, I can make that analysis at every iteration as well.
Can it derivate with respect to k? And
Yes, yes, and I will do that next, and you'll see exactly what. If you knew that the first iteration was going to be in the right direction, then you could say, okay, now which k should I stop at? And then I'll show you the expression for that next. So first, let's come up with a condition that's going to guarantee that even if I just start off, I'm going to get an improved mean squared error. Because oftentimes, in fact, it may be difficult to apply this many, many times, right? You might just want to apply it one more time. And that second time might give you a better mean squared error, and then you might stop. This computation, balance between computation and accuracy, might just say, okay, enough improvement, let's stop. Okay, so what I'm going to do now is, then let me write this as the sum, I equals 1 to n, of the mean squared error k, and I'm going to make this as a function of I. So in other words, each term here is the mean squared error of the ith component, or the ith channel, at the kth iteration. Okay? And so, like I said, it's very difficult to see how this whole thing is going to improve, but I can study this particular component and see what happens. So, to guarantee that MSEKI, this thing, goes down when I start the iteration, what I need to look at is basically this derivative, mean squared error ki dk, and I'm going to make sure that it's less than 0. Okay? When this is evaluated at k equals 0, k equals 1. So what I need to do is, there's a bunch of algebra that goes into doing this, and I'm not going to take you through that. But the bottom line is, once you write this condition out after doing this algebra, what you get is the following. You get that SNR I plus 1 lambda I to the k minus SNR I has to be bigger than 0. Okay? This is the condition you get. And now this is fine, but there's a slightly more illuminating way of writing this, which in fact will look very familiar to those of you who study communication systems. Okay, so let me just play with this a little bit and show you what that means. So if you just take this lambda k and multiply it through, what you get is SNRI lambda I to the k plus lambda I to the k minus SNRI bigger than 0. Then you just rearrange the terms here, and what you get is SNRI times 1 minus lambda I to the k less than lambda I to the k, and SNRI is less than lambda I to the k over 1 minus lambda I to the k. And then just a little algebra trick, just add 1 to both sides of this. Get 1 plus SNRI is less than, if you just add 1 to this, what this turns into is 1 over 1 minus lambda I to the k. Okay, now take log of both sides. Get log 1 plus SNRI less than log of 1 over 1 minus lambda I to the k. Okay. Now, if you've studied communication systems or information theory, what you'll immediately notice is that this is in fact the channel capacity. This is what's called the okay. So the units of this guy on the left-hand side are units of information, are entropy. Okay. So and now if you look at the thing on the right-hand side and compare it to the expression for the mean squared error here, what you will see is that this term here is basically related to, you can think of it as being related to this term or this term, but essentially what this term measures on the right-hand side is the amount of variability that you can expect to get at the output of this filter. Okay? So this term here has an interpretation as the entropy of the filter output, or the entropy that the filter allows to go through from input to output. So what this says is that if that entropy exceeds the channel capacity for that channel, then iterating this diffusion will improve the mean squared error in that particular channel. Okay? Which is a really nice and very neat result. It's very simple, right? It tells you exactly what the condition is that has to be satisfied in order for this to happen. Now, of course, this is for just one channel, right? And you might ask, is it possible to have a condition for everything all at once? Well, in order for that to happen, this condition has to be true for the same k for all the i's, right? And so it is not necessarily the case that because one channel's improvement is observed, all the other channels are going to improve as well. Okay, but sometimes it happens, and you can in fact take these conditions, and if you have an estimate of the SNR, you can compare that to the right-hand side and see if your filter is going to get an improvement. You don't necessarily have to use that estimate of the SNR for your filtering. This is just a condition that has to be satisfied in order for you to have some idea whether mean squared error is going to improve. Okay, so then you might also ask, well, if things improve, when should I stop the iteration, right? I mean, I can continue this condition for every k. Where should I stop the iteration? And then what that amounts to is basically finding the k for which this derivative is equal to 0, and then solving, taking the derivative, setting it equal to 0, and solving for the right k. When should we stop? So it turns out that if you solve, what you get is the k star for which you get the minimum is the log 1 over 1 plus SNRI to the minus 1 divided by the log of lambda I. Okay? And if you remember, the Wiener condition was satisfied when lambda I was in fact equal to this, right? So this is kind of telling you that the right k star is the ratio of these two things. Basically what it tells you is that you iterate until you are as close as possible to the Wiener condition. And as I said, you might skip it, right? Because k is typically an integer, and this is not an integer, right? This is generally not an integer. And so for instance, if you solve this, and you get that k is equal to 0.2, what does that mean? It means don't iterate, right? because k is less than 1. It says don't bother, stop. On the other hand, if you get k star is like 1.2, then it says iterate once. Okay, so you go to the nearest integer and you iterate that many times, and that's as good as you can do. Okay, and again, to be clear, this k star is the k star for channel I. Okay? So the question is, if you want to have a k star that is going to improve the overall signal to noise ratio, this is not going to give you that answer. This is only for a particular channel. So for instance, if you know, however, that your signal is mostly concentrated in a particular channel, then you use this expression and you just iterate for that channel. Right? So in the case of, if you're filtering an image, right, then you have certain spatial frequencies you might be interested in. Or if you're filtering audio, there may be certain certain audio frequencies that you're interested in. Or if you're designing a communication system and you're trying to filter a signal that's going through a channel, if you know that the signal lives in a particular part of that channel, then this works perfectly fine as far as iteration goes. Okay, so it's not as useless as it might first appear, because it's only channel specific. Okay.
Question.
Yeah.
Do you have to filter all the channels the same number of times, or can you just pick out which indices?
Right. So if you yeah, you can filter the channels separately. However, what that requires is for you to be able to break down the given signal into a certain number of channels. So remember what the definition of the channel was here. You wrote the signal Z as a linear combination of the columns of W, right? Now, because W is actually constructed, then the columns of W are going to be different depending on how you construct it, right? Depending on what kernel you pick.
Yeah.
Okay. Now, if your kernel does not depend on the data, if your kernel only depends on some fixed numbers like the xi and xj's, then the columns of W are fixed. So you can actually compute them ahead of time, and you have a basis now, and then what you can do is you take your noisy signal, you can project it onto these different components, and then filter them separately, and then combine them. Okay? So that works when W has a fixed eigenspace, basically. On the other hand, if W depends on the data, then it's very difficult to do, right? Because if you move, then the columns of V are going to change. And so you have to readjust every time. So one good compromise is that people just kind of ignore the fact that the columns of V change, and they just project things onto the, let's say, the DCT, the discrete cosine transform, or the discrete Fourier transform. And then they filter the channels individually. That's going to give you a suboptimal result, but it's better than nothing. Okay? It's better than not knowing how to proceed at all. Okay, so now that we've established some of these ideas, I want to step back for a second and give you a little bit more intuition about what this estimation procedure with kernels in this non-parametric procedure even means, and how it might behave if you want to use this procedure also for higher dimensional data. So the data that we've talked about here so far has just been one-dimensional data, right? So you've got a time series of samples. Y is just a vector that has a certain number of elements in it. And the data that we're dealing with is, everything in this course has been just one-dimensional signal processing. There's no reason why that should be the case. If you have higher dimensional data, you can just as easily do this. So one example of that might be, let's say instead of computing a pixel value or computing a particular value of a signal, you might want to compute some vector quantity, right? So the thing you're trying to estimate is not just a single number, but it's a number that is a vector that has, let's say, 3 components in it. One good example of that is in images. Every pixel is not just a single number, it's actually 3 numbers, right? Red, green, and blue components. Right? So if you want to estimate that, you've got a 3-dimensional estimation problem as opposed to a 1-dimensional estimation problem. You remember when we did this, this is a point estimation procedure, which means that you estimate 1 point at a time. And that 1 point was a scalar, so the derivatives and everything were really simple. But let me just stick to that one-dimensional case and give you a little bit more intuition about what these things look like. So recall that the estimate had the following form. Z hat of xj at any point xj is equal to the sum, a bunch of coefficients kij normalized, sum of kij over I, again this is over I, of yi. Okay? And so another way to write this is, let's just write these, this normalizing coefficient as Cj, and then we're going to write this as Cj times the sum, I equals 1 to n, Kij, yi. Okay? So if you look at this, what this shows you is that, of course, the estimate is nothing but a linear combination of the data points. But let me remind you that these Kij's were simply values of a Gaussian, right? So if I write this more explicitly, this is Cj times the sum, I equals 1 to n. When we pick this kernel to be a Gaussian, then this was 1 over square root of 2 pi sigma times the exponential minus xi minus xj squared divided by, well, let me write this as h instead of sigma, because this is what I call the bandwidth, and I don't want to confuse it with the noise variance. So 2h squared times y. Okay, so this here is kij. All right. So now, if you look at this, what is this telling you? It's telling you that the estimate at any point is simply a linear combination of a bunch of Gaussian bumps. Okay? So in fact, graphically, what this expression is telling you is that the estimation procedure is something very simple. Here's how it works. So let's say here's your x-axis. Okay? And let's say here are the data points. So here's x-axis, and here's a bunch of data points where you have values of the function. x1, x2. And I'm purposely going to draw these with non-uniform space between them. Okay, x5, and let's say here x6. Okay. Now at each one of these points, you have a data value that you've measured. So at this point, you have, let's say, y1, y2, y3, y4, y5, and let's say y6. Okay. And now what you'd like to do is to compute an estimate of z hat of xj at all the xj's, every xj in between and including these points where you have them. Okay? So how does this work? Well, it turns out, if you look at this expression, what it's telling you is at every data point, put a Gaussian with some width, and then sum everything up. So here's what you do. You go to this data point, and at this data point, you put a bump. You put a bump like this. Okay? You go to this data point, you put a bump. Okay, you go to this data point, you put a bump. Now, these are supposed to have the same variance, so I apologize for not being very artistically talented here. And then here you put a bump. Here you put a bump. Here you put a bump. You put a bump. Okay? And now, when you want an estimate, let's say your xj is, let's pick a point. Let's say your xj is over here. Okay? This xj is going to be the linear combination of all of these bumps, all of the contributions of all of these bumps added up at this point. Okay? So you're going to get, let's say, some value like that. And that's exactly what this expression is telling you. So if you do this for every xj across here, you're going to get some curve. And I'm not, I'm just kind of winging it here. You're going to get a curve that looks like that. Okay? At every point, this curve is defined by a linear combination of these bumps. Is that clear? I mean, intuitively, it is very, very simple, right? You just put a bump at every data point and you just add the contributions. You're done. End of story. Okay, so, but one thing you notice from this is that the function that you reconstruct, this whole thing, this black curve, which is z hat of x for every x that you like, basically inherits the smoothness properties of the kernel that you picked, right? So, if your kernel is a Gaussian, which is very smooth, then a linear combination of all these Gaussians is also going to be smooth, right? So necessarily, no matter how jumpy these points are, this curve is going to be smooth. Okay? It's going to be differentiable to the same degree that the Gaussian is differentiable. Now suppose you wanted to construct a function that actually had some strong discontinuities in it as well. Okay, so instead of being very smooth, what you wanted is something that had very strong jumps in it. Well, then what you could do is you could take this kernel and replace it with something that has more discontinuous nature. Okay. Now people have studied this problem of what would happen if you tried different kernels here that in fact had discontinuities in them and so on. And what ends up happening is that in practice, it turns out they really don't make much of a difference. In other words, most of the types of discontinuities that you would like to have, you can have with sufficiently many Gaussians as well. Okay. So in other words, if your data points are not too sparse, if the number of terms here is not too small, you can in fact approximate just about any discontinuity by sticking with the Gaussian. Okay. So as a matter of intuition, yes, you can replace it with some other function, but as a practical matter, generally people don't. Okay. Okay, so then there's another issue which I think is really important, which often goes unmentioned, is the notion of how many data points you typically need in order to reach a certain level of accuracy in your reconstruction. Okay? So suppose unknown to me, somebody started with a function z of x, which was twice differentiable. Okay, so in other words, it's a fairly smooth function. You can differentiate it once, and then you can differentiate it again, and you don't get any discontinuities. Okay, and the technical name for this is that it's C2, twice continuously differentiable. Okay, then you can ask the following question. If I take this twice continuously differentiable function, and I generate a bunch of data from it like this, yi equals z of xi plus ei, with this noise being just zero mean and some fixed variance, then you might ask the question, if I had the following constraint, that I wanted the mean squared error to get smaller and smaller, okay, and I want to estimate using these non-parametric techniques, how many samples should I have over some interval? Okay, so clearly the more samples you have, the smaller you can make the mean squared error between the reconstruction and the actual underlying function c of x. Okay. So people have studied, again, this question in a fair amount of detail, and what you end up getting is that the mean squared error is approximately, with these non-parametric methods, is on the order of a constant divided by n to the 4/5. Again, I'm not going to prove this to you. Okay, I'm just giving it to you as an example. So in other words, as n goes to infinity, the mean squared error collapses to 0, but it collapses at a funny rate, right? It collapses at the rate of n to the 4/5. Now let's take a minute and think back to the situation where we did maximum likelihood, right? Let's take the simplest case possible where the function underlying here, this z of x, was in fact constant, Right? So by definition, that constant function is twice differentiable. Right? So if you wanted to reconstruct that function exactly, if you wanted to reconstruct that constant, as a function of number of samples, the mean squared error in that case decayed as 1 over L when we use things like maximum likelihood. Right? Everybody remember that? So you computed the maximum likelihood estimate, and when we computed the variance basically had this decay that was essentially on the order of 1 over n. If you remember, it was sigma squared over n, right? Okay. So this is for the non-parametric estimate. On the other hand, the mean squared error was on the order of some constant, which was sigma squared in our case, divided by n. This is for maximum likelihood estimate. It turns out that this is in fact generally true even if you don't have a constant signal. Even if you have a signal that is more complicated, but it is twice differentiable, it turns out you can show that the maximum likelihood estimate essentially behaves asymptotically like 1 over n. So now you have this funny difference. You use maximum likelihood, you get something like 1 over n. You use a non-parametric method, you get 1 over n to the 4/5. Okay? This one is slower in going to 0 than that one. Why do you think that is? One estimator, I mean, they both go to 0 eventually, but one of them goes to 0 slower than the other one. What's the main difference between these two types of estimators? One is parametric, the other one is non-parametric. Right? This is assuming a model. This is not assuming a model. Okay? So in other words, starting off, this guy is saying, my function is constant everywhere. Okay? So it's making a stronger assumption about the signal. That's like having some information starting off even before you capture some data. This guy doesn't care. Okay? The estimation procedure still goes on whether that constancy is local or global. So basically what happens is that here you're starting off with more information. Here you're starting off more ignorant. But your approach is more general. Because you start off more ignorant, you pay a price. And the price is that your mean squared error does not collapse to 0 as quickly as you would for parametric methods. And this is one thing you have to deal with, right? Non-parametric methods are very general. You can apply them to just about any problem, but the downside of it is they don't give you mean squared error decay as a function of the number of samples as quickly as the parametric methods. Of course, if your parametric model for the signal is wrong, then the mean square error doesn't decay like this. Right? This is only if your model for the signal, your global model for the signal, is in fact an exact match to the true model for the signal, to the true nature of the signal. Okay, so you might ask, so this is true, these are for scalar functions. So these are for scalar valued z of x. Okay. Now you might ask the same question, particularly in this case. What happens if the quantity that you're trying to estimate, the z of x, is not a scalar, but actually a vector quantity itself, some kind of vector with n dimensions? It turns out things get very ugly very quickly. And the reason why that happens is something called the curse of dimensionality. You may have heard the term curse of dimensionality. There's sort of several different manifestations of it. One of them is sort of the computational curse of dimensionality. In other words, if you have an algorithm that you've built for one-dimensional signals, and then you want to implement the same algorithm for two-dimensional signals, the computations don't just go up by a factor of 2. Okay, the number of computations typically gets squared. They go up exponentially. Well, there's a statistical version of the curse of dimensionality as well. So for vector valued z of x, so as an example of that, You might have things like color images, where each pixel is 3 values RGB. You might be computing velocity vectors in space, etc. So it turns out that when the dimension of z of x is, some vector, which is, let's say, d by 1, okay, d being the dimension of this vector, then it turns out the mean squared error, this expression becomes like this. Asymptotically, it behaves like a constant divided by n to the 4 over 4 plus d. Okay? So the dimension actually shows up here in the denominator of the exponent. So what does this tell you? Now it tells you if the dimension gets really large, the rate of decay of the mean squared error really suffers. Okay? In other words, if in one dimension you needed n samples, in d dimensions, you're going to need a whole lot more samples to get to the same mean squared error. Okay? Now, why does this happen? So let me write this in a slightly different way. So suppose that if I want my mean squared error to be, let's say, approximately some small number epsilon, okay? Then if I set this to epsilon and then I solve for what n has to be, it turns out that n has to be proportional to some constant divided by epsilon to the d over 4. Okay? This is exponential growth, right? So the dimension, whatever dimension you're working in, you need that many more exponentially number of samples. So now you might ask, why does this happen? Okay? Why is it that we need so many more samples in d dimensions than we need in one dimension? So let me give you a little intuition for why this happens. Okay, so here's an intuitive argument for this, what we call the curse of dimensionality. So suppose that you have n data points in the interval. So here's the interval minus 1 to 1, this is 0. And suppose in here you have n samples, okay? Uniformly distributed. So in other words, with equal probability, you just picked up n samples in this particular interval. Now, I might ask the question, how many samples would you expect to get in a subset of this interval? So suppose I made a little interval here, and suppose this was 0.1 minus 0.1, okay? And I ask, how many samples do you expect are expected in this other interval, minus 0.1, 0.1. Okay? Well, it doesn't take a rocket scientist to know that this interval is a factor of 10 smaller than that interval, right? So basically you need 10 times, you need the number of samples you can expect in the smaller interval is a tenth of what was there before, right? So the number of samples in here would be n over 10, right? Okay, so this is the one-dimensional case. All right, now let's consider the case where the signal is now sitting in 3 dimensions. Okay, so now let me draw a cube. So now in 3D, suppose you have a cube like this, and this cube is sort of the equivalent of this sitting in 3 dimensions. And so that this big cube is minus 1 to 1 by minus 1 to 1 by minus 1 to 1. Okay? And now let's say I put a smaller cube in here. Okay, again, the same deal. This is the center, and the smaller cube is the red one. It's minus 0.1, 0.1. I'm going to write it like this, cubed. Okay? Okay, so now I can ask exactly the same question. I say I have n samples uniformly distributed in the larger cube. How many samples can I expect in the smaller cube? Well, the number of samples I can expect, number of samples in the red cube would be the volume of the red divided by the volume of the black cube times n, right? And if you look at this, this is, you've got 0.2 cubed divided by 2 cubed times n. And if you simplify this, you get n divided by 1,000. Okay? So in here, the number of samples you could expect in a subinterval of basically the same proportionate size was n over 10. Here, the number of samples you can expect in this guy is n over 1,000. Okay? Why? Because of the fact that there are more dimensions, what's happening is that you can expect fewer samples. So then translating this to the case where we talked about mean squared error, what does that mean? It means if you want the mean squared error to go smaller, you need many more samples, because that's how many samples you need in order to fill the same part of space with an equivalent number of data points. Okay? All right, so this is a problem that's very commonly encountered. People design algorithms that do a great job, and they give you very nice performance on one-dimensional signals, and they simply fail to give you adequate performance in 2 dimensions. So this is one fundamental difference between doing signal processing and doing image processing. You just cannot take a one-dimensional signal processing algorithm and just slap it on a 2-dimensional signal and expect it to work. This is one of many reasons why. Okay? So if you have not had a whole lot of respect previously for people that work on 2 and 3 and n-dimensional data, this should give you a little bit of an idea that it is actually quite difficult, because there are so many more degrees of freedom in higher dimensions. Okay. So now so we've talked about one way of trying to improve these estimators, z hat equals w times y. Let me give you an idea of another way to do this. So this is another approach to improving z equals wy, or z hat equals wy. Okay, so this other approach is something that many people have used over many years, and they've given it many different names. Okay, so remember that the approach we used before, we called it diffusion. This one has had the following names. It's been called residual iteration. It's been called twicing. This name was given to it by John Tukey, who used to be, he's no longer alive. He was a very famous statistician in the 50s. I think he died in the 80s or 90s. So this is John Tukey. Has anybody ever heard of the Tukey window? Use the window-to-window data? Same guy. Okay, another name for it, Bregman iterations. Yet another name for it is reaction diffusion. Now, for those of you who have done physics, you know that diffusion is, like the heat equation. Stuff diffuses in a medium, and reaction diffusion is a diffusion equation that has a counteracting force that is stopping that diffusion for some reason. Okay, so it turns out this has that physical interpretation. I hope I have a little bit of time left to tell you about that. So here's what the iteration is. It looks like this. Z hat k plus 1, just k, equals z hat k minus 1 plus w times y minus z hat k minus 1. Okay. So let's see what this is. This term here is called the residual. What this is doing is you filter the signal, you get z hat k minus 1. Then you look at the difference between the filter signal and the data. Okay? And you apply the filter to it again, and you add it to the previous estimate. If the residual had no additional information in it, then this term doesn't do anything, right? So this basically tells you, just like the iterations before that updated things, if you remember, we talked about Newton's method, we talked about Newton-Raphson and so on. This is the update, so estimate is the same as the previous estimate plus a correction. Here, the correction is related to what we call the residual signal. Okay? And of course, we need to initialize this, and the initialization here is z hat 0 is equal to w times y. Sometimes we refer to this initialization as a pre-filtered data. In other words, before what we did was we just applied this once and we stopped. This iteration just, hey, don't stop. Use that as your 0th order starting point, and then run this iteration forward. Okay? And the name for this is sometimes the pre-filtered signal. Okay, so let me give you an example of what this does in a more specific sense. Let's do this for k equals 1. So z hat 1 is equal to z hat 0 plus w times y minus z hat 0. And I just plug in the definition here, w times y plus w times y minus wy. This becomes 2w minus w squared times y. Okay? So before, when we iterated the diffusion, you got w squared, w cubed, and so on. Here, you're getting other polynomials. Okay? So the second iteration is not just w squared, it's 2w minus w squared. It's a polynomial that, in fact, has coefficients in front of the terms that might be negative. Okay, so yet another way to write this is 2I minus w times y. Okay, I'm just factoring things out. Now this is actually kind of interesting to look at, because if you look at this part, what it is, it's just one iteration of the diffusion, right? Which does what? It blurs, right? So this blurs, or averages. There's some kind of weighted averaging. Okay? What about this guy? If W is an operator that does averaging, it means it's basically like a low-pass filter. Like it's an adaptive low-pass filter. If W is a low-pass filter, what's 2I minus W? What kind of filter is it? High-pass, right? So this, in fact, is a high-pass filter. So what did diffusion do? Diffusion applied low pass again, low pass again, low pass again, until what happened? The constant signal came out. Okay? What this guy does is it does one low pass followed by a high pass. And then if you do it again, it's going to do another low pass followed by a high pass. Low pass, high pass. Okay? And the low pass and high pass are not exactly the inverses of each other, right? So they're not canceling each other out. This does a certain amount of blurring and a certain different amount of high-pass filtering to give you the next iteration. Okay? So what this ends up doing, and this is, by the way, the reason why it's called the reaction diffusion equation as well. With diffusion, things continue to diffuse. What's happening here is that at every iteration you get diffusion, and then you're kind of pushing against that diffusion back, which is this high-pass component. Okay? It's interesting to also look at the asymptotic behavior of these two different filters to see what you get. So here's some important differences. First of all, let's look at them asymptotically. remember for the case of diffusion, you had the limit as z goes, k goes to infinity of z hat k. This is the limit as k goes to infinity of w to the k times y. And if you remember, w to the k basically converges to a rank 1 matrix, which was 1 times u1 transpose, where u1 was the constant row. This times y, and this is a constant signal. Okay? All right, so now what about this residual iteration? Let's see what happens to that. So the iteration is this. Z hat k equals z hat k minus 1 plus w times y minus z hat k minus 1. Okay? If you take a look at this, at convergence, z hat and z hat k minus 1 should be equal, right? So if you set these equal, we cancel, you go away. So at convergence, what you have is z hat, so the limit as k goes to infinity, z hat k is y. Okay. In other words, if you continue to iterate this residual iteration, what you end up getting back is your original data with noise and everything. Okay? Whereas in the other case, if you continue to iterate, you would get a constant signal back. So the steady state behavior of these two filters is completely different. Now, why is it intuitively that you get the original data back? Because this iteration, what it's doing is it says, okay, this iteration equals to the previous iteration plus a bunch of detail. This is details that I have extracted from the residuals, right? Okay, so if you've done a perfect job, what are the residuals? They're just noise, right? Now, so if you keep doing this, what you're saying is, okay, I'm going to take more detail out of the residuals, more detail out of the residuals, until there's no signal in the residuals anymore. All you're taking out of the residuals is noise. And you continue to add that back to your estimate, what do you expect you're going to get? You're going to get the original signal back, because you've just slowly put in all the noise back into the signal. Okay? Okay, so this is one difference. What about the mean squared error? So let's take the diffusion case. Let me just write down the mean squared error expression for k. Sum I equals 1 to n lambda I to the k minus 1 squared a0 I squared plus sigma squared lambda I to the 2k. And for the residual iterations, I'm not going to show you the proof for this. You'll have to trust me. 1 minus lambda I 2k plus 2 a0 I squared plus sigma squared 1 minus 1 minus lambda I to the k plus 1 plus whole thing squared. Okay, so again, this term here is the bias. This term here is the variance, or bias squared. And correspondingly here, have the same thing, bias and variance. Okay. Now, in this case, remember I showed you that the bias goes up and the variance goes down. That's why you end up with a flat image at the end, or a flat signal at the end. Here, the exact opposite happens. Here, the bias, in fact, goes down and the variance goes up. Which makes sense, because at the end, what do you end up with? You end up with the noisy image, which has the most variance in it. Okay. So these two things, these two iterations, are not just, there's the differences between them are really fundamental. Okay, the trade-off between the bias and variance is completely different. So you may be faced with the question, now, if I have a filter that I've designed, which is W times Y, and I want to improve it, which one of these two iterations should I use? Should I use the diffusion iteration, or should I use the residual iteration? And what is the condition that I need to keep track of to decide which one of these is the better one to use? Well, again, I'm not going to take you through the math, but here's what it gives you. The condition is the following. Log, well, you saw it earlier, whether you saw it in one direction. SNRI, log of 1 over 1 minus lambda I prime. I'll tell you what that is in a second. So if the inequality is this way, you use diffusion. The inequality is that way, you use the residual iteration. Okay, this is exactly the condition that I showed you for this case before. So it turns out that if this is exactly the reverse, what you want to use is the residual iteration. And if they're equal, of course, toss a coin. Okay. Now this lambda I prime, this, I just want to be clear, this is the ith eigenvalue for the corresponding method at the kth iteration. So in other words, the lambda I is not the same for these two different methods. Okay, because one of them, lambda I simply goes to lambda I to the k, and in the other case, it doesn't. See, if you look at this term, for example, just forget about the square, then the lambda I to the k is the behavior of the kth eigenvalue, the ith eigenvalue at the kth iteration. Here, if you forget about the square, the eigenvalue here, lambda I turns into 1 minus lambda I to the k plus 1. Okay, so that's what this lambda I prime is. It's lambda I to the k in this case. The diffusion is 1 minus lambda I to the k plus 1 for the residual iteration. Yeah.
It seems intuitively that the diffusion equation just loses our data information, so why should we even use it?
Well, what the diffusion equation does is that it's very good at suppressing noise, right? Because you design these adaptive low-pass filters and you keep applying them. So I guess what you're asking is, why should I ever use this equation? So there are going to be two conditions. Let's say you design your filter W, and your filter W can have two different forms. One is that it is very, very good at getting rid of noise, but it's not very good at preserving the details of the signal. Okay? So what happens then is when you apply the filter, then in the residuals you're going to have a lot of signal left over. Okay? So in that case, it's intuitive to use the residual iteration, right? Because the residual says, hey, wait a minute, you didn't do a very good job. The residuals still contain a lot of signal. I'm going to take that signal back and add it to my estimate. Okay? So that's one kind of filter. It's very good at blurring, but it's not very good at preserving the signal. Now, if it's a filter like that, obviously applying diffusion is a bad idea, because it's so bad at blurring, it's so bad at preserving the signal that you apply it twice, it's even worse, right? But the opposite can also happen. In other words, you could design a filter W using some kernel definition that is very good at preserving signals, but it's just not a very good denoising filter. Okay? In other words, it's so sensitive to the signal, to slight changes in the signal, that it tries to preserve everything. Okay? So what it does is it just doesn't do anything, not much of anything, with any kind of discontinuities, including ones that may happen to be noise. Okay? So in other words, the filter on the first shot, it's just not very effective. Okay? It's very conservative. So then if that's the case, you want to use diffusion. diffusion will improve its performance. That's my intuitive description. This kind of gives a mathematical description for that. Is that helpful? Okay. Okay, so the last thing I want to say about this, and we have, by the way, don't run off, we have to do the course evaluations. I'll give you, whatever, 10 minutes to do that. The last couple of things that I want to say have to do with interpretations of all of these non-parametric methods in sort of comparison to things that we've already done. Okay, so what have we already done? We've done parametric things with maximum likelihood, with maximum a posteriori, with Bayes mean squared error, and so on. So you might ask the question, how is all of that related to this? Is there a way to interpret what we're doing with this simple weighted least squares non-parametric business in terms of these other methods? It turns out there is an interpretation which gives you an idea of why it is that these non-parametric methods work as well as they do. So let me give you a sort of brief introduction to that. So suppose that I write a very general description again like this. Yi is z of xi plus ei. And I'm going to assume that these are again zero mean. I have a bunch of data values I equals 1 to n. And now let me be very general and assume that xi and yi are both random variables, okay, that come from some probability density function, or samples, these IID samples, from some PDF, p of x and y. Okay, this is a joint distribution for the positions where you took samples and also the value of the samples themselves. So basically, your samples don't have to be uniformly distributed. They can be any distribution here. Okay. Now the thing is, in the non-parametric framework, we don't actually know what this is, right? But let's put that aside for a second. Let's say we know what this is. Okay, so now suppose with this description I wanted to estimate z hat at some position x using the Bayes formulation. Okay, what's the Bayes formulation? Z hat x is expected value of y given x, right? You compute the conditional density of y given x, and this becomes your estimate. Okay, let me write this in a slightly different way. So this is the integral of y, p of y given x, dx, right? Okay.
dy.
Oh, sorry, dy, yes. Okay. Okay. And I can rewrite this still in a different way. I can write this as the integral of y, p of x, y, the joint density, divided by p of x, dy. Okay? And p of x is the marginal, which is nothing but the integral of p of x and y over y. So I can write this as the integral of p of x and y divided by the integral the xy dy times y dy. Right? Or let me be a little bit more tidy and write this as the integral p of xy times y dy divided by the integral p of xy dy. Okay? So far so good? All right, so now remember what the formula was for my regression. Z hat of xj is sum wij yi, right? Okay, so if you simply compare this expression to this expression, what you see is they're fundamentally the same. What this is, it's a linear combination of the y's with some weights in front of it. The weights happen to be the conditional density of p of y given x. wij in this expression, this is just a discrete version of this. Wij, therefore, essentially plays the role of this conditional density. Okay? Yet another way to look at it is, let me rewrite this as the sum Kij yi divided by the sum of Kij, right? Now compare this form to this. Again, the same deal, right? So what you see is that Kij is playing the role of this joint density function. Okay? So the whole point of this non-parametric business is that the choice of the kernel is essentially trying to mimic the behavior of this unknown probability density function between x and y. Okay? We don't know what it is. All we're doing is we're struggling to somehow model this dependence, model this statistics by using a kernel. Now remember what the kernel does. The kernel measures the distance or similarity between a point and another point. Right? Now those points could be xi and xj, or it could be xi and yi and xj and yj. Right? So it's measuring similarities, it's measuring distances. Those distances, when properly normalized, are nothing but essentially a probability density. Okay? What is the simplest way in which you estimate a probability density from a bunch of samples? You do a histogram, right? What's a histogram? You take the domain, you break it up into a bunch of bins, and what do you throw in those bins? All the samples that are really similar, right? Similar in what sense? In the sense that they fit in this little interval, right? That's what you do. That's exactly what this does. Except that what we use here, we don't use bins, and we don't just throw things inside a bin that are close to each other. We add them together with a smoother weight. Okay? In fact, the histogram is the simplest example of a non-parametric estimate of a probability density function, where the kernel functions that you're using are simple rectangles that don't even overlap with each other. Okay? So that's exactly what this is, except that we use more complicated functions. All right, so this is one way to see the relationship between what we're doing and what the Bayes mean squared error. Okay, so let me just write this here. This is the Bayes mean squared error estimate. Now, if you remember, we had another way, a completely different way of dealing with the Bayesian analysis as well, and that was to use the maximum likelihood and maximum a posteriori formulations, right? So let me show you how these are similar. So now let's look at Bayes maximum a posteriori, or MAP. Okay, so without getting into the derivations, if you remember, z hat arg min over z, 1/2 the norm of y minus z squared plus lambda over 2 times some penalty function, which I'm going to call r of z. Right? So this is basically, if you ignored this part, this would just be the least squares. But now you're adding this part, so this is a penalized least squares. But another way to think about it was that this corresponded to Gaussian noise, and this corresponded to a prior on your signal z. Okay, so prior information, which is why we're calling this maximum a posteriori. So now my question is, how does this relate to these things? Okay, in fact, how does this relate not only to these things, but also to the iterations of these things that we did, which improved the estimate one iteration after another? It turns out the relationship is, it's a little bit tricky, but ultimately it's not very difficult to see. So let me just take this description and simply try to minimize it using an iterative mechanism. which uses steepest descent. Does everybody know what steepest descent is? So steepest descent is simply one version of these optimization algorithms that we talked about. All you do is you take the estimate and you compute the gradient of the cost function, which is this cost function, and then you update your estimate in the direction in which the gradient is changing the fastest. Okay. So it's basically, if you want to understand gradient descent, if you've ever skied, you've done gradient descent. Okay? You're on top of a hill, and you want to find the fastest way down. Okay? So wherever you are, you compute the derivative all around you, and you look around, and where the derivative is going fastest, you go in that direction. Okay? So here's what it looks like. Z hat k is equal to z hat k minus 1 minus mu. This mu is called the step size. We'll get rid of it in a second. And z hat k minus 1 minus y plus lambda times the gradient of r at zk minus 1. Okay, so this is nothing but the gradient of this whole cost function. Minus mu is just the step size, it's just a scalar, and this z hat k is your previous iteration. Okay, now we can normalize so that this step size doesn't really play a role. We can just say that's equal to 1. Okay. All right, so this is, I'm calling it SD, steepest descent. Now let me write down the other iterations that we used to improve our estimates, right? So let me write down the residual iteration. What was that? That was z hat k equals z hat k minus 1 plus w times y minus z hat k minus 1, right? And the diffusion iteration is z hat k equals z hat k minus 1 plus w minus identity z hat k minus 1. I've written this a little bit differently. I've added and subtracted a z hat k minus 1 because I want to write these guys exactly in the same form as this. Okay, so if you just get rid of these, then what you have is simply w times z hat k minus 1. Okay, does that make sense? Okay, so now I want to see how these two correspond to this guy. And it's very easy to do because all I have to do is I have to compare the right-hand sides. Okay? Z hat k and z hat k, let me set those to be the same. Now I just compare the right-hand side of this to the right-hand side of that, the right-hand side of this to the right-hand side of that. Okay? All right, so if I compare for the residual case, what I get is I'm going to compare them, and then I'm going to solve for this regularization term and see what it gives me. Okay, so the gradient of r zk, or zk minus 1, is minus 1 over lambda, which is this coefficient here, times w minus I times y minus z hat k minus 1. Okay? And for the other case, for the diffusion case, it's a little bit more complicated. This gradient of r zk minus 1 is 1 over lambda w well, it's just w times y minus z hat k minus 1 minus 1 over lambda times I minus w times y hat. Okay. Oh, sorry, y. Okay. So what I want to do is really, all I'm interested in is for what value of r of z will I get equivalence between my non-parametric formulation and this formulation. Okay. So what I have is I have the derivative of r, or the gradient of r is equal to this guy, or the gradient of r is equal to this guy for this other case. So if I want to solve for r, I have to take the integral of both sides of this. Right? And it turns out you can't take the integral of this right-hand side unless w minus I is positive definite, it turns out. Okay? But let's say that's true, that there's, this is a technical condition that has to be satisfied. Because remember, if you remember from your vector calculus, this r is a scalar function, right? So this is the gradient of a scalar function, which means that the right-hand side is a vector field, but because it's the gradient of a vector of a scalar function, it has to be curl-free. Okay? And the fact that it's curl-free means that w minus I has to be positive definite. Okay, but that's kind of a red herring. We don't need to deal with. Okay, so if you solve all of these things for r, what you end up with is the following. For the residual case, r of z turns out to be 1 over 2 lambda y minus z transpose w y minus z. Okay, this is for the residual case. And for the diffusion case, you get r of z equals 1 over 2 lambda, again, y minus z transpose w y minus z plus 1 over lambda y transpose I minus w times z. Okay, yeah.
This RZ is the function that the residual method is the same, would be the same as the steepest descent method.
This is the function that if you took this function and you plugged it in here, okay, then this function, optimizing this function and iterating it using steepest descent would give you the same answer at every iteration as the residual iteration. Okay, and if you plugged in this other one, you would get the diffusion. Okay. Now, what's interesting about this is that if you look at this, this is a prior, right? This is what we're calling a prior. Right? That's what this is prior information, right? Except that it's a kind of weird prior information because it doesn't just depend on the signal. It also depends on the data. Not only does it depend on the data through y, it may also depend on the data through w. Okay? So, what we call this is in the literature, this is called naive Bayes, or empirical Bayes. In other words, you don't know the prior information exactly, but you approximate it using something from the data itself. From the given noisy data, you approximate something like the prior, and then you use it to set up a map estimate, or the minimum mean squared error estimate. Okay? And this is the general, if you look in the literature and you're interested in learning more about this, look under empirical Bayes or naive Bayes. It's naive because, you know, you're just doing something very simple, very naive, using the data. Okay? And these two are, of course, very different. Interestingly enough, the residual actually corresponds to a much more tidy expression, whereas this one has this one and another term. And in fact, if you look at this is somehow like a correlation between the data and the z that is unknown. Okay? So, to summarize everything we did the standard parametric methods, which included maximum likelihood, maximum a posteriori, Bayes minimum mean squared error, least squares, and so on and so forth. And then we did all the non-parametric stuff. And then I showed you how the non-parametric stuff is related to the parametric stuff, but how these extra terms are in fact not standard. So there's not an exact equivalence between the two. It's equivalent only in an approximate sense. Okay? All right, so I think this is pretty much where we should stop. The next lecture, I'm going to do a review, unless anybody has an objection and you want to hear more, new materials. So I'm going to do a review of everything so far and also solve a bunch of problems, essentially a practice final. Okay? So any other questions?
Can you post the homework for next week?
Yeah. Post the what?
Can you post the homework? It was forbidden. Or
Oh, it
the
was?
practice exam.
Oh, the practice exam. Okay, yes, I will post the practice exam, yes. But I know the homeworks are all posted. So please don't leave, because I have to give you these evaluations to do. Let me get my activator here. Okay, I need a volunteer to take these back to the office. Would somebody like to do that? You know where to take them? Okay. So these are some of the other questions that you need to answer. What's the travel? Okay. Let's see.
This week's homework?
I'm sorry?
This week's homework?
It was due on Tuesday.
Yeah. Dude,
No, this one. I'm talking about this one. This one was incomplete. I thought you were giving me that one. Okay, yes, you got your homework. Give it to me now before I leave. Okay? Are we all set? All right.
No, don't think so. No. Since you have another, so you have your last one. And you will increase much of numbers in the midterm. So
we have two quite exactly. And one of them is due this week.
Thursday.
Last one is due this Thursday.
No.
There's
We have
no-
just one homework this week. The final for next week.
Okay. But the bar doesn't have enough. Just the last one. That's the final. Do you know how to
Still,
print?
yeah.